please introduce yourself and your company and what solutions, what problems you are solving in this space.
Sure. So my name is Oskar Zdunek. I'm business developer manager at ScanWay, and ScanWay is an optical company. So what we doing, we measure everything with light. So that as we see us, so we're providing optical payloads for Earth observation, but not only, mostly for satellites, rockets as well, and the different spacecraft. And not only big cameras, but also some smaller cameras. We have also one industry part of the company, but we focusing there mostly on this quality control in some industry, industrial manufacturing and everything. So regarding space, we are doing these optical payloads from small one up to big one. We have two kind of products lines. So the ScanWay optical payloads. So the telescopes, as you can say it. So the camera systems that can observe from bigger distance, like from orbit, from low Earth orbit to can do some pictures of the Earth. But we have also a line where we are focusing on some exploration stuff. So we're providing optical payload for moon observations, for example, from moon orbit. We also providing cameras for some. We can provide some camera for space situational awareness, space domain awareness, as well some mm, in orbit servicing, in orbit manufacturing, so checking of something from orbit, in orbit, if everything went correctly or not. Uh, that in abbreviation, also like this ScanWay, the second line is ScanWay camera system. That's mostly using for what we are using for this in orbit servicing, for example. That the set of smaller cameras where you can check, for example, if your antenna was deployed correctly from the satellite or the solar arrays was deployed correctly. If there is some malfunction, we can also provide those cameras with some basic processing algorithms. So the camera can check the health of the satellite, for example, if there was some impact of the micrometeorite, or if something went not exactly as planned, and can send you some information if there is some malfunction. So that's what we're doing. We also provide that small camera, for example, for Ariane 6 maiden flight. We were observing the separation of fairing and deployment of the satellite from the Ariane 6 rocket. That's what we're doing mostly. And in the telescope area, we're providing from small one, like 1 unit CubeSat size telescopes, up to big one. The biggest that we right now providing is 450 millimeters aperture telescope. That's around 50 kilograms with all of the temperature control systems and everything. So that's the big telescope for big satellite, 150 up to 400 kilogram satellite.
Okay. And was there how long has ScanWay existed? And was there something that changed? Was there a particular mission that you needed to solve a problem for? How did ScanWay come about? Why does it exist now?
Sure. So we are 10 years on the market. The first project that we did that was I think the stepping stone for the ScanWay was the project that our member of the board did in Rexus Bexus project in European Space Agency. So the students they were observing the drilling in microgravity, how the drilling in microgravity will look like with the cameras. And that was the first starting point for ScanWay, and also the first space project. So we started with the space. After that, we also did some industry stuff, but the first project was the space one. And we are more than 10 years on the market. In January, we had 10 years of the company. So now it's 10 years and a couple months. What we also did, we achieved a lot, to be honest, because I think the best starting point for getting more and more projects in the space area was our idea to send our demonstration satellite with our telescope in January 23. So that was, I think, the best, I must say, After that project, after that mission, we were more recognizable, and we got more and more questions and queries about our payloads. We got a flight heritage on that mission for our camera and also our optomechanical structure. But what was important was the camera, because what we wanted to achieve by this mission, we wanted to de-risk a couple of stuff, especially the electronic part, because it's the most crucial in space after all, with the radiation and everything. So we developed our own camera around CMOS sensor, and by that mission we gathered a flight heritage. But what we did, we also used the same focal plane array and same camera in other missions that we launched later. So I think that was like the one of the milestones uh, when we got more and more projects in the space area. So I think that, and also what we achieved, we entered alternative Polish stock market in 23, so the smaller market called New Connect. And after 3 years, this year we debuted on Warsaw Stock Exchange, the main floor. So that was our journey mostly.
And is there, so you've mentioned a few things there. Is there something particular about your cameras that is different to other cameras that existed beforehand? How is that different? Why is it important?
Okay, I think we have a couple of advantages, because what we did and what we're still doing, we always designed our telescope in a sense that we can easily change some of the parts or do some delta development. So, for example, if we have one telescope, we designed it in a sense that we can easily change focal plane array, so the camera at the back of the telescope, to put different camera with different, for example, wavelengths. Like we have one optical payload 120 millimeters aperture with our camera, with camera from different providers in visible spectrum, but we have also shortwave infrared camera that we can put at the back of the telescope. So I think that's our advantages, that we can easily change and adapt to the requirement needs. And what we also did in the past, and we're still doing that from time to time, we are not afraid of taking new projects that needs some development. Like, of course, there's a couple of companies that have optical payloads and they selling just that payload. They don't do nothing, and not they don't do much development. They don't do much new stuff. And we see that it's really needed, because sometimes customers coming to us and they have like really strict requirements. They need something like that or something like that, and that can't be met with our existing telescope. So we're trying to find the right solution for them. For example, like with this changing of or focal plane array, for example, of implementing different camera at the back of our telescope. So that worked. For example, in the moon mission, we providing telescope with one of camera from different providers, but that was when we checked when we did the trade-off, we checked that camera will be perfect for moon orbit and for making the pictures. Yeah, so that I think that's our advantages and what we see as our advantage.
Okay. So maybe spend a couple of minutes as well just telling me who would use your products, who would purchase your payloads, what kinds of industries, what kind of companies. Is it private sector? Is it government? Give me an idea of your client base.
Like that was also our goal from the beginning, that we don't want to be the company as many other company in the Europe, especially, that focus only on the grants and only on the European Space Agency projects. We want to be really commercial company from the beginning, and we succeed in that area. So most of our projects are commercial one. Of course, we're doing some of the European Space Agency stuff because it's obvious that there is a money there is some money that Poland put in European Space Agencies. So we of course have some projects there as well, but that's not like our strategy. We don't want to be focused on the grants and on the public money. We want to do more commercial stuff. But of course, if we are talking about bigger payloads and bigger systems, then some private companies don't have that much money, so sometimes the government's coming to us as well, and also some bigger projects. So to be honest, it depends on the scale, what will be the mission and how big it will be, because of course we're working with private companies, but when, especially in the now, like we see a lot of trends in the making some national constellations to be more resilient. It's really booming right now. So a lot of governments even asking us, because they have their own constellation projects for big satellites to have national capabilities to for Earth observation. So they coming and asking about the bigger payloads, of course. But it's not that obvious also, because when you have some emerging country, they don't know much sometimes about the optical payloads, of course, because
Mm.
it's not that common topic. So they asking sometimes a lot of questions, and we also, what we do in our everyday work, we also learning customers a lot, teaching customers a lot, what could be possible, what can be done, what can be done in that use case that they have, because from time to time they coming with really, with the requirements that can't be met with existing physics, to be honest. So the physics don't allow us to go into some direction because of the diffraction limits and everything.
Mm.
And I think that a lot of like some parts of the offers, when we sending them, it's some of them are teaching what can be done, to be honest, in that kind of requirements.
Right. I mean, you mentioned the Ariane 6 rocket earlier. What are some of the most exciting projects that you've been involved in, and how, what were the kind of some of the details of your product, and how did it help those missions?
I think one of most exciting for me is and will be, because it will be flying this year, somewhere around half of the year. Will be flying to the moon orbit with intuitive machines, because we will be mapping moon and some resources on it with our telescope from the orbiter from intuitive machines. So that will be really exciting, because that's new for us even, making pictures of the moon. And what we also doing in the project, we providing whole data pipeline. So we also processing this data from the moon, and in that area we connecting exactly what we're doing in those two branches, like this industrial part of ScanWay and space part of ScanWay, because the industrial part is really great in processing of the data. So we connecting two branches of ScanWay and doing whole processing data pipeline with the pictures that we will be taking of the moon, and making this and checking these minerals and everything. So that's a great project for me. As well, we have one project with Korean partner called Nara Space. We doing telescope to observe the methane emission from orbit. So they want to map Korea and check how the methane emission look like from orbit. That's also really good for example, for taxation purposes, because the government don't have a lot of tools to check if the factory is putting the right amount of the methane that they're producing every year. If they put the right amount of the governmental sheets for these taxation purposes. So the satellite coming with help and can check exactly if they put the right amount there, if they exactly producing this much methane.
Great. That's a really good example of kind of the differences as well. So you've got one telescope looking at the moon, one in orbit looking down at Earth. So are those different products? Those are different cameras, and how do they differ? What are the details that make those differences possible?
Especially like for the project where we will be checking the methane, it's more like the spectrometer. We will be checking in shortwave infrared, because there is some peaks in shortwave infrared where we can spot methane. In the moon project, we will be looking in couple of bands in the visible spectrum to spot some minerals on the moon. So that's different in a sense that that will be the different wavelengths of the spectrum, and we will be checking a little bit different stuff, but also making a pictures of the Earth with bigger telescope that we even doing it's also a little bit different because that will be just RGB, also visible spectrum. So every project is a little bit different, to be honest. But I like really when they have some like concrete, some nice use case where we can check something really viable for Earth or for our partner.
And so those differences, though, do they take place in the hardware, or a lot of it is done in kind of the data processing afterwards?
I think both, because of course the data processing will be different. Like for the shortwave infrared, when you're checking the pictures that is in visible spectrum, you can see it because it's like normal picture. And when you have in shortwave infrared, that's much different one. So what we also providing in that telescope is like dual telescope system. We have one spectrometer in shortwave infrared, but we also have on the same optical bench the small telescope for visible near infrared spectrum. So we have like two pictures aligned where we can put the mid animation on the picture that you can see itself. So it's much different in that sense because when you see this picture in shortwave infrared, you don't know what's happening on that picture, to be honest, because it's not what we used to. So that's for sure different, and it's different hardware, different sensors, different class of the telescope, and everything around it. I think it's different. So not only the data but also the hardware.
And so talk me through maybe the process. If I come with maybe a climate change project or something, and I want to monitor something on Earth, how does it start with you guys? What's the process? How do you work with the client? What sorts of things do you need to understand before you can create a payload that would work?
Sure. Like, so especially we want to understand what use case do you have. So if you have like, I don't know, maybe observing some mineral on the earth, then we want to find, especially in some probably scientific database, what wavelengths will be perfect for that, in which wavelength we have some peaks, that can help us to spot that right material. And then we provide proposing some system, especially which resolution do you want to have, exact um, how exactly you want to see the pictures, with what resolution, from in which size of the swath of the picture. So like 10 kilometers per 10 kilometers, for example. So it depends on the a lot of stuff, to be honest, because like the most common parameters is mostly like what wavelengths do you want to have. So RGB, so the visible spectrum, red, green, blue, mostly. That's the common question. What wavelengths? What will be the GSD? So ground sample distance. So the resolution. Ground sample distance is like if you have 1 meter GSD, it's like 1 pixel on the picture that we did, it's like 1 meter on the earth, mostly in abbreviation. So that's also really valuable parameter that telling you what you will see on the picture with what quality mostly, and if this 1 pixel on the picture is 1 meter on the earth. Exactly. So that's also, and also the swath, so the um, how many kilometers per kilometers or meters per meters would picture have in the end. So that's also available because when you, for example, observing some environmental stuff like the ice in polar areas, then you want to have big probably swab like 10 kilometers, 10, 100 kilometers per 100 kilometers. But when you spotting a car, that will be too much. So then you need probably some 5 kilometers per 5 kilometers. So it also depends, and that also influence the whole system because uh, the swath is like when you have the sensor that making picture, you have the megapixels, right? 100 megapixels of the sensor, or you have if your phone 50 megapixels. So that's the pixels per pixels on the sensor itself. It's also like that sum up to these kilometers per kilometers, and the second parameter, the GSD, that's what influences the GSD, the pixel pitch of the sensor. So how small the pixel, 1 pixel of the sensor is, that influences the GSD. So it's not also that common because there is not that much sensors in the air, in the whole world. So I think that when it will be still evolving, when we will have more sensors existing from, I don't know, Sony or someone who's making the sensors, we will have also more possibilities in our area.
Mhm.
So that also influence us, the technology development in that sensor area. If that's CMOS sensor or CCD sensors or different sensors, that also influence us.
All right, got it. Yeah. So, and that brings me on to a connected point. What kind of demands are you seeing from customers or clients, and how does that speak to maybe some emerging trends as to what kind of how this industry is evolving and moving, and how does that affect your product line?
Sure. So I think that now the trend is these big telescopes. As I mentioned, with these governments, like everyone want to have some resilience and have their own country capabilities in the Earth observation satellites. So that's a big trend right now, especially after war in the Ukraine. I think that's emerging a lot. A lot of countries see that they need some resilience, that they want to have their own satellites to be able to spot something. So that's the trend, to have big satellites with really nice resolution. But also now the trend is for some these space situational awareness or space domain awareness, because in Europe it's mostly space surveillance, space. Yeah, in US it's mostly space domain awareness, and in Europe it's mostly space situational awareness. I don't know why the difference, but yeah. So I think that's also the trend, because there is more and more people who want to do pictures from satellite on orbit, the picture of the other satellite on orbit
Mm.
or other object on orbit. So that's mostly this SSA SDA application, and that's also bringing a lot of new technical difficulties, because when you doing some pictures on orbit, there is like mostly dark areas, so you have to have telescope that can gather as much light as possible from the distant objects. So that's bringing a lot of also technical difficulties to find the right parameters, right telescope to spot something from distance, to check different satellites, also even to make a pictures of that, because everything is flying. It's not like making pictures on Earth when you have
Mhm.
something on the spot. It's still moving, to objects that moving in different probably directions, so it's not so easy as well. So I think that's the trend, and also exploration is also a trend, because we see more and more interest in that lunar area, and more customers asking about some lunar stuff, and we see more and more projects, because it's getting more easy to do some exploration, moon exploration projects.
Mm. And so, final question from me today, actually. Do you have any products in development at the moment that we can look forward to later this year, next year, over the next 5 years? What are you kind of working towards?
Sure, like probably the biggest telescope that we are building, it's still not yet ready. It's still in the development. It should be ready next year probably. So we're waiting for that, but that's also not like the stopping point for us, because we want to go to even bigger telescopes, to have like less than 50 centimeters resolution, GSD resolution. So that's the goal for us probably. But when you going toward the bigger telescope, everything is changing, because you have to align your clean room, everything. Mostly, then you integrating telescope not horizontally but vertically, because it's much easier, and especially with this kind of big mirrors and everything. So there is a lot of adaptation in our clean room happening even right now. to be able to do some stuff like that.
And is that development connected to a particular mission or project, or that's just something that you want to kind of develop because you know there will be a demand later?
It's more like we see that there is already a demand and some of the customers asking about that. And that's our goal to go into that direction, because that will be the highest resolution telescopes, that the class of the highest resolution telescope that everyone would like to have.
Sure.
Yeah.
Sorry, and just finally, give me the advantage of a higher resolution. What kind of, like you say, if you're looking at Antarctica, you don't need such a high resolution, presumably, but in what cases might you need a very high resolution?
Especially like the disaster management, the military stuff as well. You can spot, for example, some of the plates of the car, like with higher resolution. You can spot the plates of the car. You can do that with some high resolution telescope or low resolution telescope. So everything like that, and also this disaster management, that's really needed. It's also connected to the revisit time, of course, when you have some big constellation, because when you're doing some disaster management, you have to have this information really fast and really updated. So everything is connected. But yeah, with this really high resolution, you can do a lot of more stuff, especially to help government tackle this disaster that happened, for
Sure.
example.
Great. Oskar, thank you so much for your time